All right, so how much work is done by the force of gravity in the car? Let's consider the directions. We have a force and a displacement. Well, the car is going, the car is going up the hill. Excuse my drawings. This is the displacement. And the force being applied by gravity. Let's go with blue to represent the force. That force is going to be straight down. Gravity pulls things straight down. So what is the angle between those two things? Well, if we used, let's go yellow for another line. We know that this horizontal line is in there. And that horizontal line with this green line is 25 degrees. And this is a right angle. So the angle between, let me put a letter F down here so you know that this is the direction of the force gravity. What would be the angle between these two? What is this angle? Oh, what color didn't I use? Red. What is this angle right here from the green line to the blue line? Well, this one's 90 and that one's 25. So what is 90 plus 25? That would be the angle between the two. So let's get our formula. Work is force times distance times the cosine of the angle. The force is the weight, which is up in a problem. A 13 broken down car of mass 13 kilograms. A 13 kilogram car, that's like a matchbox car. That's just a little toy car. Why is he pushing a little? Anyhow, 13 kilogram toy car times gravity gives you the weight of the car times the distance he moves it times the cosine of 90 plus 25, which gives us 115. So straight from left to right, type it in, and you should get negative 15,000 joules of work in order to do that one. All right, let's go back to our derivation. We talked about on the right-hand side, we found work. If we sub in that W for work, work is force times distance. On the left-hand side, what is that? That is what we call kinetic energy. Kinetic energy of an object is equal to 1/2 times the mass of the object multiplied by the speed of the object squared. Its formula looks like this. This is called the energy of motion. The energy of motion, if we look at the units for this, it's going to be a kilogram for the mass, and this V is in m/s. Squaring that gives us kilogram meter squared second squared per second squared. Well, a kilogram meter per second squared, if we can pull that out, a kilogram meter per second squared is a Newton. We have two m's. If we put one in this grouping, we would have a Newton time. Wait, we just talked about that. Work is force times distance. That's the same unit. So joules is the unit for kinetic energy. It's also the unit for work. How about that? All right, so let's work our kinetic energy formula. Determine the kinetic energy of a roller coaster car that is moving at a certain speed. So this kilogram number goes in for the M, and this 18.3 meter per second number goes in for the V. And it's just a matter of typing it in from left to right. You're going to get a big number, 5. Let's see here. There's 2, moving it over. So this is 105,000 joules, 105,000 joules, moving it over 5 spaces. That's what that means. So this is 105,000 joules. Let's look at another one. A comet with a mass of this strike. There it is again. Just throw the two numbers in here. Ooh, watch out, I see a K in there. So for this one, you got to throw this kilogram number in for the M. And this, what are we going to do with that little K? That little K actually means and can be substituted out for times 10 to the third. So switch that to times 10 to the third. Now, make sure you're careful when you're squaring that. It needs to be, the whole number needs to be inside parentheses, and then you press squared. So see if you can get that 2.45 times 10 to the 20th number on your calculator. But that's a straightforward calculus. So on the left, we have kinetic energy. On the right, we have work. And this together is called the work energy theorem. So the work energy theorem is derived from this third equation from constant acceleration and F equals ma. Remember, we solved for F equals ma, solved for A, and threw it into that equation. So we mixed those two up and got the work energy theorem. So now let's put it together. The work energy theorem says that the work done on a system is equal to the change in energy. So here is the work done on this hockey puck. So what would be the change in the hockey puck's energy? Well, the change in the energy is going to be the same thing. The change in the energy is going to be 0.675. They're equal. The work done on a system is equal to the change in kinetic energy. Well, if we sub in that formula for the change in kinetic energy, we can get the change in velocity of the puck. The change in velocity of the puck will be, wait a second, will be 3.59 meters per second. Remember the square root. This v has a squared there, so you got to square root your answer. All right, power is the rate at which the external force changes the energy of a system. Is represented by this formula here. Power is equal to work divided by time. So work is force times distance, and if there's an angle, it's force times distance times cosine of the angle. But another formula, you're just dividing. So okay, there's two W's here. Now you got to be careful with the two W's. This is a symbol in an equation, and we're throwing the units into the symbols. Remember, work and kinetic energy, all energy is measured in joules. So you got work converted into joule, or the unit would be joules, times unit would be seconds. When you take a joule divided by a second, you get a W unit, which is a watt. So this W represents the unit, and this is the symbol in the equation. And you got to keep that straight. So a watt is a relatively small unit of power. It is about the amount of power needed to take a drink of water. So a lot of times you'll see kilowatts used. A kilowatt, remember, is 1,000 watts. All right, so let's look at this couple problems. To finish this section up, we have an electric motor lifts an elevator 9 meters in 15 seconds with a certain force. So power is work divided by time. Remember, work is force times distance. The Newton number goes in for the force. The distance is 9 meters, and they are in the same direction. Electric motor lifts an elevator. Yeah, it's applying force upward. The elevator's going upward, same direction. We don't need the extension cosine of theta. Divided by the time, and we get our power. So you can represent this answer as 7.20 or 7,200 watts or 7.20 kilowatts. Either way is fine. All right, let's look at another one. A box that weighs this much is lifted a certain distance straight up by a cable, again in the same direction. The job's done in 10 seconds. What is the power? So the Newton number goes in for the force. This distance number goes in for the D. The meter number goes in for the D. And the time in seconds. We got to stick with SI units, meters, newtons, and seconds. Multiply divided by 2, you get 1150. Or take away 3, move that decimal 3 there. We got 1.15 kilowatts. Is there a hard one here? Let's try this one. A winch is designed to be mounted. We got a Newton number given. We got a kilowatt. Watch out. Multiply that by 1,000. That would be 300. And we got a distance. So when you plug that information in here, this kilowatt number is your power. So that's 300. This is 300 watts goes in for the P. We have this Newton number goes in for the F. We got this going in for the D. And the unknown in this equation is the T. So if we cross multiply, imagine this being over 1, we would get T equals, well, this thing times T equals that product times 1, and then you'd have to divide each side by this 0.3. So in summary, we derived the work energy theorem, which gave us a formula for work, and it gave us a formula for energy. Newton's second law and equation 3. And we have an equation for power, which is work divided by time. So that is section 1010.